Welcome you all in the today's lecture of embedded system. In the last lecture, we have talked about task scheduling. We have divided this task scheduling into two major categories, that is clock driven and another was priority driven, right? Priority or event driven. So in clock driven we have studied about endless loop, and basically endless loop was just an operating system, right? So there was no kind of scheduling, just automatic schedules, right? But there were two major category in the clock driven, that was table driven scheduling, and another was cyclic scheduling. So in the table driven scheduling, uh, you know so in table driven scheduling there is a scheduler table, right? So there is a scheduler. So in the table driven there is a scheduler table, right? So every time it schedules it. So for example, you have a task here, okay? So there is a task T1 which is executed for, let's say, 10 millisecond, right? So another task could be started at this time, okay? Immediately another task can be started. So let's say this is for 8 millisecond, another task could be for 5 millisecond, right? So every time the scheduler has to wake up, okay? Every time it has to set the timing for the next task, right? And these both the types of scheduling are static scheduling. So we know already the arrival time of the task, and those are periodic. So what is the period of those tasks? So we know all those informations about the task. So already tasks are scheduled with their details in the scheduled table, right? So whenever the task is arriving, okay, whenever the task is arriving and it is released, it can be executed if another task is completed, right? So the major disadvantage in table driven scheduler is that you have to set the time every time, okay? So the scheduler wakes up here, then set the time for the next task, then scheduler after completing this task again it will wake up and it will schedule for the next task. However, in the cyclic scheduler, the timer is set once, okay? Suppose that here the start timer has been set, okay? So timer will not again it will not start, right? So you have fixed the time. So let's say you have fixed the time of 10 millisecond. So every time scheduler will schedule the next task, okay? There is no timer which will be set explicitly. So the timer, if you set it for let's say 100 millisecond or 50 millisecond, that is called as major cycle, okay? And there is another timer, that is a period, right? So every time it has to just schedule the next task. So it will see the schedule table and it will execute the next task, right? So this major cycle is divided into equal number of frames, and these frames should be, the frame length must be, so this is your major cycle and this is your frame, let's call it as f. So f should be integral multiple of your major cycle, right? So what is the disadvantage in this case? So very nicely, let's suppose one task is coming here, okay, and its deadline is after this another frame, right? So what is happening, within this frame you cannot execute this task, right? Because the deadline will be missed in this case, right? And second thing is, let's suppose that one task has arrived here, okay, and it has been executed here, Okay, so you see that this space is vacant, it's idle, right? So this space is vacant here, so there is a wastage of time. Okay, so let's say that your frame length is let's say this is your frame length. Okay, so this frame length is here and one task is arriving here and it is executed here. It has very less runtime and it also has very less runtime, let's say. So what is happening, a lot of time is wasted. You see, this time is wasted. Okay, so in cyclic scheduler the disadvantage is that a lot of time will be wasted. However, the advantage is the timer the timer set overhead is less. Okay, the timer set overhead is less in cyclic scheduler, right? So we have kept in the last class like what should be the major cycle. The major cycle should be major cycle or hyper period should be the LCM of all the periods, right? So one task, second task, so execution time of n task, right? So suppose you want to execute n task in one major cycle. So major cycle should be the, suppose this has your 20 millisecond of your execution time, this has 30 millisecond, another has 40 millisecond. So your major cycle should be LCM of those three, so that should be 120 millisecond, right? Also, the another condition was that your frame size should be the integral multiple of your major cycle period, right? So this criteria sets the lower bound for this one. Okay, the lower bound for this one, lower bound on frame. Okay, this is for major cycle, and your frame must be integral multiple of that, right? So frame, what could be the frame? Frame could be the, so 120 millisecond is your major cycle, so you can take any integral multiple of that. Okay, but it should be larger than the execution time of any task in the given major cycle, right? So your F must be greater than, the frame size must be greater than maximum of execution time of any task, where E1 to En are the execution time of all the tasks, right? Okay, and there should be at least one frame, right? Otherwise what will happen, there should be at least one frame between the release. So suppose you are your this task is releasing here and it should be completed within the deadline only. Okay, so arrival means arrow is upside. Okay, arrow is upside and this is the deadline. So there should be at least one frame between between the release and the deadline of the task, right? So these two conditions are important for deciding the frame length. Okay, so these two are the basically the types of clock driven schedulers, and the disadvantage of clock driven scheduler is it cannot handle aperiodic or sporadic tasks. Okay, and it cannot provide a preemption also. Preemption means suppose the high priority task is coming, so preemptive task means suppose the low priority task is running and some high priority task came. Okay, so in preemptive case what will happen, this will stop the low priority task and high priority task will be started executing, right? But in the non preemption case, first the low priority task will be completed and then only high priority task can be started. Okay, another task can be started in the non preemptive scheduling, right? So your clock driven does not support preemption scheduling also. So now we will start the second type of scheduling, that is event or priority driven scheduling. Priority driven scheduling. So what is an event or priority driven? So priority driven means there is some priority associated with the task, right? So suppose you have a task T1, so it has some certain priority, okay, and T2 has also some different priority. So there are priorities which are assigned along with the task, right? So how to handle these tasks? Okay, so for event driven scheduling, the scheduling is performed whenever the new task will arrive. It is not defined offline. Okay, so in uh, event case the scheduling is done when the task is ready or a task has arrived. Okay, and another is when another task is completed. Another task is completed. Okay, so what is the meaning of that? So let's say that this is your task T1 and it is, it has started finishing your executing here, right? So here this task has executed. Okay, so now the scheduler wakes up here. So this is the scheduling point for an event driven or priority driven scheduling, right? So here the scheduler wakes up and it checks that which task should be executed next. Okay, so another one condition should be the task should be ready. Another condition is the task is completed. So these are the scheduling points for event driven schedulers, right? Now now the question comes that who decides the priority? Who decides the priority? So who decides the priority of which task should come or should be executed when, right? So your operating system can decide or your scheduler can decide the priority. Okay, so scheduler can decide the priority in different ways. For example, you can schedule the task which has shortest or basically shortest execution time, right? Or your a scheduler can decide a schedule the task which has come first serve, right? So there are many things which we can schedule it now. So these event types of or event driven schedulers are categorized into two broad category. Okay, so these are categorized into two broad category. One is static event driven scheduling and another is dynamic event driven scheduling, right? So what is a static means we know that the priority before itself. Okay, so static means we can say that your designer or programmer assigns the priority before scheduling itself, right? So suppose you are designing any scheduler, your programmer has assigned different priority to different tasks, right? But in dynamic case the priorities are decided in runtime. Okay, so whenever the tasks are running and depending on different criteria in the runtime or during the runtime only the task is scheduled, right? So for example, you can schedule a deadline you can schedule a task whose deadline is near, right? Or you can check the least stack time for the task, right? So depending on that you can schedule the task dynamically, right? So this is the basically major difference between static scheduling and dynamic scheduling, right? So first we will see the static scheduling. Okay, so first we will see static scheduling. Okay, so in static scheduling as we told that scheduling is, or the priority is already decided offline, right? So programmer has already decided the priority of each task, right? So there is a famous scheduling algorithm for that. So that is known as a rate monotonic algorithm. Okay, so what is rate monotonic algorithm? Although there are some other algorithms which are having some minor variation as compared to rate monotonic, right? But we will study rate monotonic, which is most widely used, right? So uh, so here what we assume, as we are talking about a static priority, so we assume that there is no shared resource. Okay, so what is the meaning of that? So so two tasks are executed or sharing the same resource, and then it is difficult to schedule, right? But we are not assuming that there is any shared resource. Then we are assuming the tasks are periodic. Okay, we will handle aperiodic task and sporadic task. So that cannot be, sporadic means we don't know actually whenever it will come, right? So programmer cannot decide about the sporadic task, right? So it should be allocated dynamically, right? It cannot be done in static scheduling, right? So you assume that tasks are periodic. These are not sporadic or aperiodic. Or sporadic, right? And your job deadline or task deadline is the end of period. End of period means another job can be started once the deadline is completed, right? And here another, as compared to clock driven scheduling, what is the difference here? Here all tasks are preemptable, right? Preemptable, right? So there is some priority, so they can preempt the current task and they can start executing, right? And there is something called a laxity of a task or slack of a task. So what is that? So let's say that this task has started executing here, and it execute in a time E, let's say E, and this is the starting time and this is the deadline of the task. Okay, so it has executed even before the deadline. So this period is called as laxity or slack of a task, which is defined as Ti equals to Di. Okay, so let's say that for a I task, so execution time is Ei, okay, and the deadline for that particular task will be Di. Okay, so this laxity is defined as Di, the deadline, minus T plus Ei. So T is the starting time and execution time is this one. So Ti is the laxity time for that particular task. Okay, so now what is actually this rate monotonic algorithm? Okay, so rate monotonic algorithm means, as the name indicates, it schedules based on the rate. Okay, so what is the meaning of rate? So as I told that these different tasks, T1, let's say T2 to Tn, has different periods, right? So it has certain periods, P1, P2 and Pn. So what is the meaning of period? That T1 repeats after P1. Okay, so every P1, T1 is repeating. Same, every P2, the T2 is repeating, right? So these are the periods. So rate monotonic algorithm says that you schedule the task or give the priority based on the rate. Okay, so rate is nothing but 1 upon period. So period means if period is less, that means the rate of the task is frequent, right? So you assign the priority based on the rate. Okay, so the task which has higher rate or less period, you assign the high priority to that task. Okay, you assign the high priority to the task, right? So let's take a small example. So let's take 3 tasks. So this is one task. So let me take 3 tasks here, 1, 2 and 3. Okay, so your T1 task is having a period of 4 and execution time of 1. So I am denoting any task Ti with the Pi and execution time Ei. Okay, so it has a period of 4 and execution time of 1. Okay, so and T2 I takes as the period is 5 and execution time is 2, and T3 I takes as execution time is 7 and the period is 7 and execution time is 2. So let me divide it into 1, 2, 3, 4, 5, 6, 7, 8, right? So what is the meaning of that? So T1 started executing, so T1 is having the lowest period. Okay, if you see that T1 is having the lowest period, so what is the meaning? So T1 is having the lowest period means it is having highest priority. Okay, so T1 is having highest priority, then T2 is the next priority, and third one is your T3 priority wise, if you talk about priority. Okay, so T1 means it has to start first. Suppose all 3 tasks came simultaneously. Okay, so let's say that this task also arriving at the same time, this task is also arriving at the same time, and this task also arrived at the same time, right? So which one will be executed first? Whose rate is high? So it will be executed here. Okay, then what is the period of T1? It will repeat after 4. Okay, so this is 1, 2, 3 and 4. So it will repeat again here. Okay, so here this is done. Okay, so it will T2 can start executing here. Execution time is 2, so it also it has executed between 1 to 3, right? So still I have a space because till here it's vacant, right? Processor is vacant. Here you have to assume that only we are using one processor. Okay, so processor is vacant, so now T3 can start executing. Yes, so T3 execution time is 2. Okay, but T1 has arrived here again, so I cannot execute because I am not executed completely. So I have executed this half only. Then preemption, because rate monotonic scheduling is just a preemption based scheduling. So when T1 has highest priority, it will stop the execution of T3 and it will start executing here. Okay, then again T2 came because T2 next period is at 5. Okay, so T2 came now, then also T3 cannot be executed, right? So it has to wait until this completes. Okay, and after 4, T1 will come at 8. So 6, 7 and 8. Okay, so here again your T1 came and it is coming after every 5, so let's forget that one. So yeah, here when will you complete it? Okay, so it completes till 5 to 7. Okay, and 7 means T3 again came here. Okay, so what happened? This T3 has missed the deadline, right? Because another T3 came, it has repeated. So your T3 has missed the deadline. Okay, so given the task, you should know that these tasks are schedulable for a given period and execution time, right? First we have to define the something called schedulability. Schedulability means, given the period and execution type of any task, we should determine that the task can be executed or not. Okay, because in the last case we have seen that your 33 has missed the deadline. We cannot schedule it for the given period and execution time. So now what can I do? So this schedulability, first I have to check the schedulability. Okay, so how can I check the schedulability? So there is a formula for computing the schedulability. So that is given as for all tasks I equals to 1 to n, where n is the number of tasks. Okay, so ei, the execution time of a certain task, divided by the pi. Pi is the period of that task, right? That should be less than n times 2 to the power 1 upon n minus 1. So this is the condition for schedulability. Okay, so what this condition says, that if your task for a given period and execution time of the task, if this condition is satisfying, that certainly you can execute or you can schedule these tasks, right? So please note that this condition is your sufficient condition. This is not necessary condition, this is a sufficient condition. Sufficient condition means if it is satisfied, if this condition is satisfied, that certainly you can say the tasks are schedulable. Okay, but if it is not satisfied, you cannot guarantee that it cannot be schedulable. Okay, it could be schedulable in that case also, but if this is satisfied, you can say that this task is schedulable. Now we are not going into proof of this one. If you want to study the proof, you can read the paper by Liu and Leyland. Okay, so there is a paper in the response time analysis. Okay, so we will see this condition is satisfied for our given example or not, right? So yes, what is this actually? Ei upon pi, that is called as utilization. Okay, so let's say if I compute the utilization for a certain task. Okay, so let's say your period is 4 and your execution time is 2. Okay, so my period is utilization is 50%. So if there is no other task, I am scheduling it within the leftover 2 time unit, then I can say that utilization is 50%, right? So if I compute the utilization overall for all tasks, I have to sum it. Okay, so this is the utilization. Okay, so now I'll take this is satisfying for our given example or not. So what was our given example? So this is the schedulability. So let me write again the formula. Yeah, so for the T1 task, if you go back, so T1 was 4-1, so execution time was 1 and period was 4. So what is that? 1 upon 4. For the next task, it was 2 was the execution time and 5 was the period, and for the third task it was 2 by 7. So if you compute it, you will get around 0.95, right? So what it says, that it should be less than equal to n times 2 to the power n 1 upon n minus 1. So n is 3 because there are 3 tasks. So 2 to the power 1 by 3 minus 1. So this is your 1.26 minus 1, and this is 0.78. So you say that utilization is 0.95. So is it violating or not? So this condition is violating the, okay, this condition is violated here. Okay, so you are not sure that this can be executable. Okay, so we cannot say that given the period and execution time of these tasks, you can certainly schedule these tasks or not. Okay, but I cannot guarantee that I cannot, if this condition is not satisfied, I cannot schedule the task. So what I will do, if I go back to the previous example, okay, so here what I do here, instead of 7, if I take the period as 10, okay, if I take the period as 10, this will go at, this is 8, this is 9, and this is 10. So here it is repeating here. So what I can do, this leftover portion can be executed here. Okay, then only T1 came. Okay, so it can be executed. So if I just change the time period of third task to 10, I am able to execute, or I am able to schedule all the 3 tasks, right? So if I take 10 as a period, so I will check this condition is still satisfying or not. Okay, so what I did here, I changed the period of the third one, so the rest of the things will be same. It will become 2 by 10. So what will be this one? 1 by 4 is 0.25, 2 by 5 is 0.4, and 2 by 10 is 0.2. So this is 0.85. If you see, this must be, the condition says that this must be, schedulability condition says that this must be less than 0.78, but this is still violating. Okay, this condition is still violating, but still I am able to execute or schedule the task. Okay, so this is the sufficient condition. Okay, so now we'll take one more example. So let's say that I define a 2 tasks, T1 and T2. So T1 has a period of 4 and execution time of 2, and T2 has period of 8 and execution time of 1. So what will be the utilization? So if I compute the utilization, that will be 2 by 4 plus 1 upon 8, that is 0.625, right? So this should be less than n times, so n is 2, number of tasks are 2 to the power half, so that will be root 2 minus 1, so this will be 0.82, right? So this is already less than, so in this case it is satisfying. Okay, schedulability condition is satisfied. Okay, so I can certainly say that these 2 tasks are schedulable. Okay, so how can I schedule it? For example, if I want to schedule this task, okay, so the period is 4, right? So both came here. Okay, T1 and T2 both came here, and let me write, this is 1 2 3 4 5 6 7 8 9. So the period is 4, so this is 1 2 3 and 4, so again it will come here. Okay, T1 will come here again, so it has time unit of 2, so here it will execute. Okay, then this is free, then T2 can be executed, and the execution time is 1. So here T2 is executed, then still I have some idle time, and where process is doing nothing. Okay, so then again T1 will come, it will execute for 2 time units. Okay, and then it has 8 anyhow, so if I write it 1 2 3 4 5 6 7 8. Okay, so second task is coming here. Okay, but so this is, let me write different names. So T1 also coming here and T2 is also coming here. Okay, so now you have vacant place here, so you can execute T2 here. So let me execute T2 here. So still you have vacant space where processor is doing nothing. Okay, so what will be the utilization in this case? So if I compute the utilization, here it was, what was the utilization? 0.625. okay, so when there are two tasks, in this case utilization is low, so I could still increase the utilization. How will I increase the utilization? I can accommodate one more task here if it is possible. Okay, so if I draw a graph, okay, so graph says that suppose you want to schedule n number of tasks. If n number of tasks are increasing, utilization will become saturated. Okay, so let's say this is your 100% utilization. When the utilization is 1, so it will saturated, and it comes around 0.69. how it comes, we will see. So your utilization is defined as summation of ei upon pi, and that must be less than equal to n times 2 to the power 1 upon n minus 1, right? So if your n is going to infinity, so suppose you want to assign infinity task, okay, so your this side will become simply log 2. okay, the side will become log 2, so it comes around 0.69. so if your n is very large, okay, so this is becoming this is approximated by log 2, and this is coming somewhere around 0.69. so your utilization cannot it is going down when you are increasing the task. Okay, is that clear? So what we can say, that your utilization is bounded by this number. Okay, when your nr or n is going to infinity. Okay, so this was all about the rate monotonic algorithm. Okay, so in the next lecture we will study about the dynamic scheduling, and we will take an algorithm which is based on earliest deadline.